So continuing on number 23, I have to finish this part B. Describe a sequence of similarity transformations that would map one onto the other. Now we're off the graph, so we can't talk about rotating or translating a certain amount, anything like that. We're going to have to use our descriptors such as angle bisector, perpendicular bisector, things like that. So what I'm going to do is, what I'm seeing here is I need to line reflect because of orientation. I've got to find a way to get E up to matching the orientation that B's in. So right now, A to B to C is going in a counterclockwise direction, while its corresponding points are going in a clockwise direction. So the way to fix that first, and I always do this first, is I'm going to line reflect. I'm going to line reflect triangle CDE because I have to map this one onto that one. Be careful of that. So I'm going to line reflect triangle CDE over, this is weird. I'm going to do this so that it'll match right away, but you don't have to think of it this way. There's other ways. I'm going to say the angle bisector of angle C. Now here's what that's going to do. That's going to perfectly map E over to here to make E prime. That's going to perfectly map D over to here, D prime, because the angle bisector, it'll force that to go right there. If we reflect over the angle bisector, it'll force it. Force this right here, if I do it right. Okay? Now, what that does is it fixes orientation, but it still aligns E prime on the same line as C, E prime, and B. This is great because when we dilate, points move collinear, right, on the same line that the center is on. So the fact that C, E prime, and B are all on the same line is going to help our dilation a lot. Okay, so now we're going to take and we're going to dilate triangle C prime, D prime, E prime, centered at C by a scale factor of, now you could probably get away with saying a scale factor that maps E prime onto B, but I'm going to do this. I'm going to take image, which it needs to be CB, over pre-image, which is C, E prime. Okay, this should map E prime onto B if we did it right. Now just think right now, it's an enlargement, and CB is bigger than CE, so if we put CB over CE, it should be the right amount. Okay, that should map one onto the other. All right, next one, number 24. So these arrows are showing parallel. We're probably going to use alternate interior angles theorem, but let's find out. Let's highlight exactly which one we're after here. We want these triangles, the bow tie problem. Okay, so we're going to, let's see, I see the Z here, backward Z. All right, so those angles right there are going to be congruent by alternate interior angles theorem. So are these. Might as well use both of those. So then the triangles are going to be similar by angle, angle. Again, that's most of ours. So let's go through that. One, I need TV parallel to XP because it's given. Then I need to follow it up with alternate interior angles. I'm going to say angle VTY congruent to angle XPY and angle, so now we're going to go TVY. TVY is congruent to angle PXY because, now you guys can say alternate interior angles theorem. I'm going to say when parallel lines are cut by a transversal, I'm going to write it all out is what I'm doing. When parallel lines are cut by a transversal, alternate interior angles are congruent. You can shortcut that by saying alternate interior angles theorem. Okay, now I have the triangle similar. Triangle TVY is similar to triangle PXY by the angle-angle triangle similarity postulate. Okay, so now describe the sequence of similarity transformations that would map TVY onto PXY. So here's what that's going to look like. First move, I'm going to point reflect triangle TVY through point Y. Okay, so here's what that's going to accomplish. T, when we point reflect, we go straight through the point the same distance away. So whatever TY is, that distance is going to go right there. So this is where T prime lands. So that those are the same. V is going to do the same thing. V is going to land right there. And we're going to get that new triangle. Okay? Then all we got to do is dilate it centered at Y. So then we're going to dilate triangle T prime, V prime, Y prime, centered at Y by a scale factor. Now again, we need to know that it's an enlargement. We have to enlarge that smaller triangle. So we're going to want to put a bigger number over a smaller number. Now, I'm going to go image, which is YP, over pre-image, which is YT prime. That's it. That's going to make it bigger. So recognize that you have to enlarge this smaller triangle. So you have to use a scale factor that's bigger than 1. All right, that's going to do it. Okay, get a couple of these done. All right, if triangle RST is similar to triangle PQW, which of the following is true? The corresponding sides are in a ratio of 4 to 1. That's going to be true because 20 is to 5. You can reduce that. Take out a 5. So we have that 4 to 1 ratio. So that's going to be true. So that's, yeah. Corresponding angles are not in the ratio of 1 to 4. Corresponding angles are going to be congruent. Angles, no. Angles half as large, no. So it is just choice A. Okay. Which polygons are always similar equilateral triangles? For sure, because no matter how big they are, their angles are 60 degrees. And all the sides are the same. Maybe they're all 8s. For this one, it's all 60s. Maybe they're all 5s. So they're always similar. Parallelograms don't have to be. You can stretch one out more than the other. So corresponding sides might not be in the same ratio. You know, you might get an 8 here and a 10 there, but you get an 8 there, a 20 there. Those are not going to be similar. You can do that with a rectangle. Trapezoids, there's all different shapes even, so that's a no. All right, which pair of triangles must be similar? Two isosceles triangles with congruent vertex angles looks good, right? So if you're isosceles with the same vertex angle, say it's like 40, the base angles are the same. So I'll calculate those. Yeah, you're stuck with 70 apiece. So if you know the vertex angles are the same, you know, and they're isosceles, you know they've got to be similar. Two right triangles, no. You can have 45, 45, 90. You can have a, say, 30, 60, 90. So you don't. Two obtuse triangles, same thing. You can just change those other two angles. They don't have to match. In fact, you don't even have the same obtuse angle. You can have one with a 100-degree obtuse angle, one with 110. Two scalene triangles with congruent bases. Again, what that means, really simple. You might have, say you have 10 on this one. You could have 10 on this one too, but you could make those other angles look completely different. Okay, you could do this. I mean, these aren't going to match. So you have an 80-degree angle there, but a 90 there. Those are not, those just don't have to work out. So then that would be, say, 30. You're not going to have corresponding angles congruent. So it's definitely going to be A. Okay, getting there. You want to draw an enlargement of a design that is printed on a card that is 4 by 5. Okay. Just going to quick draw this. It's 8.5. Oops. By 11. What are the dimensions of the largest complete enlargement you can make? We could swing this over, right? We could swing this over to 5 and 4 here, right? Okay, so basically which one? Complete enlargement. So what can we multiply this by so that we still fit on the page? Okay, so here's what I'm going to do. This is going to be a little bit weird. All right, 5 times what can get up to 11? Now what we'll do is we'll test that. We'll get the number there. So that's 11/5, right? So one scale factor we'll try is to map the 5 all the way to the 11. The goal is, will that number of a dilation, will that scale factor, should say, still keep 4 inside of that? Okay, it's a little bit tricky. So we're gonna divide by 5. Okay, so the scale factor we're going to use for this is 11/5, which is 2.2. Now, if we take a scale factor, the same scale factor, 4, if we multiply that by 2.2, we get 8.8. That's going to be too large of a scale factor, meaning we are off the page. Okay, if we make the card fit all the way this way, it's going to be too wide. Okay, it's going to go out of bounds. On the direction, the 4 is going to just be too big. So we can't go all the way with a scale factor of 2.2. That's too much. Let's try the other one. 4 times what will get us 8.5? Okay, what scale factor could that be? So I'll go grab that number. 8.5 divided by 4. That's going to be 2.125. Now that scale factor still stays under this one. So when we scale up, so to speak, or dilate by that scale factor, the 5 is not going to come off the page. It's going to come up just short. So our scale factor that we need would be 2.125. Now what we're going to do is we're going to take our 4 by 5, and we're going to multiply by this scale factor. So take both of those numbers, 4 times 2.125 is 8.5. Okay, that's going to be 8.5 is what I get there. 5 times 2.125 it's going to be 10.625. Now, if we change those to fractions, that's 8.5, and that's 10 and 5/8. Okay, that's this one. Pretty tricky problem. Okay, we tried scaling up 5 to fit it all the way there, but that would have been off the page with width. So we take the width, go all the way to 8.5 with it. It'll come up just short on this direction, the length. So we're good. We still fit on the page. All right, let's finish this off on the next video.